Start.
So, hi, today we'll be covering our lecture on kernel methods. So first I will do the review of what we did in the last class and how kernels automatically fit in what we are doing currently, and we'll see further motivations on how kernel methods are really useful in pattern recognition, and then we'll see the limitations of linear models and kind of motivate kernel methods even more. Then we'll see how kernels are identified to be a valid kernel, which is using the Mercer's theorem. We'll see what it means to be a valid kernel, and then we'll do the kernel construction. So in last class, what we had seen were we had seen two motivations of using kernel methods. We had seen that when we were doing kernelized SVMs and the optimization of dual regression. We've seen that the kernels came in very naturally. So
can I see clearly?
Huh?
The word is too small.
Oh, this one? Okay. So in both in SVMs and dual regressions, we saw that kernels came in very naturally. So given a set of data points I equal to 1 to n data points which lie in Rd, what we saw was if we map these data points from Rd to some R zeta, where zeta is much greater than d. In that case, what we can write is our phi is equal to phi x1 transpose. We form this matrix, and then during the derivation of dual regression, what we found that this term always occurred together, phi and phi transpose. So then we substituted this as k and called this as the Gram matrix. This Gram matrix is nothing but an n cross n symmetric matrix, where each element of this matrix can be written as function of xi and xj, this can be easily seen from this that the I comma jth element of the Gram matrix is phi xi transpose phi xj, and this is the ijth element of k Gram matrix, and this gives us what we call as the kernel, and this is what we call as the kernel function. This is what is formally called as the kernel function in pattern recognition. So it's a mapping from of 2 points in Rd and gives a similarity between xi and xj. So now we'll carefully look into what it means to be a kernel function. When is it called a kernel function? When is it a valid kernel function? But before that, let's look into the motivation of that. So earlier what we did was linear models. We saw that optimizing the weight vectors for linear models was very efficient. So this was a huge advantage with linear models, but the biggest disadvantage with linear models is that you can learn only very simple decision boundaries. So consider this example here. let's say our D is 2, so X lies in R2, and we have 3 points. This is 0, 0, and 1, 0, and 0, 1. So 0, 0 lies in negative class, and 1, 0 and 0, 1 lies in the positive classes. So from our linear models class, we know that we can easily find a hyperplane that can separate the negative class from the positive classes, right? So this was the biggest advantage, and we could learn this hyperplane very efficiently. But now, if we were to add now let's say you added one data point to this. This was the earlier data points, and you added one more data point here, which was 1, 1 from, and the class of this is negative. So these two are the negative classes, and these two are the positive classes. So now, can you identify which line separates the two classes? Does there exist a line which can separate the two classes? Any cases? Can you draw a line where we can separate the two classes? Is there a possibility?
No.
There's no way you can draw a line which can separate positive classes on one side and the negative classes on the other side.
You need two lines.
You need two lines.
Or a curve.
or a curve. So curves are nothing but the non-linear models. But then the problem with non-linear models is it's very hard to optimize for them. Learning two lines is again a combination of linear functions. So what do we do in this case? So this is the biggest limitation of linear models. Although it's very efficient to learn those models, but it can learn only simple boundaries like this. But anything that's complex here, like here, cannot be learned. So now consider this mapping. So let's just consider this mapping. The kernel function k takes an input x and z both in R2, takes the inner product of the two and squares them. So when I expand this, what it becomes is, so this I've just expanded the inner product of this and written this here, and then it becomes right. So now this can be written as transpose so you can immediately see that these are exactly the same. Right? So the inner product of inner product is nothing but x1 square z1 square plus x2 square z2 square plus 2x1 x2 z1 z2. Right? So this is exactly the same. So what we have done here is we have taken a point x1 x2, and through an implicit mapping, what we have done is we have mapped it to a three-dimensional function, three-dimensional three-dimensional space. And this is how the mapping looks like. It takes a point x1, x2 and maps it to x1 square, x2 square, root 2, x1, x2. Right? So now how does this help? So consider the example that we were looking at. So 0, 0 gets mapped to 0, 0, 0. And 1, 1 gets mapped to 1, 1, root 2. Similarly, these were the negative classes, and these are the positive classes. It gets mapped to, right? So now if you try to plot this in 3 dimensions, this is a negative plus, positive 2, the 2 points, positive points, and the third point lies somewhere here. It's 1 comma 1 comma root 2. So this is x1, x2, x3. So 1 comma root 2. So it lies somewhere here. So now you can immediately find a hyperplane that separates this with this and this point. So the linear separability is immediately achieved by this mapping. Right. So what we have achieved is the linear separability. And hence we can identify linear models that can separate the two classes. So this is the intuition behind kernel matrix. So what this kernel function did was it identified two the input to this kernel function were two data points in R2. It mapped it implicitly to a very high dimension phi x and phi z, right? And then took an inner product in that space, right? But the point to be noted is that while we defined x comma z, we did not know this mapping, and we only defined it using x and z. So this is what a kernel function does. A kernel function takes two inputs, maps it implicitly to a very high dimension, and then takes the inner product in that very high dimension. And the best part is we don't even need to know this implicit mapping phi. So this is a huge advantage in pattern recognition. You can see that even linear models can suddenly start identifying complex decision boundaries, right? So now the question is, what are valid kernel functions? So one question is, can I define any function that takes two data points as an input and call it a kernel function? That doesn't seem to be true, right? And so there should be some kind of properties that a function should satisfy for it to be a valid kernel. By validity, what I mean is implicitly there exists this phi which maps the data points into a very high dimension. Although we might not know this mapping, but implicitly there should exist a mapping. So that's what we call as the valid kernel. Although we might not be able to identify it explicitly. So this is when we call a kernel valid. So this was one example. We saw the example of this polynomial. This is called the polynomial kernel, and there is another well-known kernel function x comma z, which looks like the Gaussian function, and is called the RBF kernel. And the interesting part in this kernel is that the implicit mapping here is to the infinite dimension. So it takes x1, x2 and maps it to an infinity dimensional space. But we don't need to know the mapping, and we can still compute this similarity between x and z. So this is again a huge advantage. We'll see how, specifically when we revisit SVMs, we'll see how it comes as very, very useful thing. And then, so now to identify what is a valid kernel, there is something called the Mercer's theorem. So first I will write it very formally, which is if and only if for any non-zero function f that is square integrable any non-zero f that is square integrable and satisfies the following property. And so you take any non-zero function that is square integrable and integrate this equation, and if this is satisfied for all choices of f and then the kernel is called to be a valid kernel, and then there exists a mapping phi. So we'll not do the proof here, but implicitly what it means is the gram matrix that you have that you create should be positive semi-definite. So this should be satisfied. So this is what Mercer's theorem says, that a mapping phi exists only when you take any function f and this property holds, then there exists a phi mapping and an expression like this. So we'll not do the proof here, but instead what we will look into is how do we construct valid kernels. So the biggest problem with this Mercer's theorem is that although it specifies things very clearly, but identifying a valid kernel K is very, very hard. It's not trivial to identify if a kernel is valid or not. And till now, only these two kernels have been identified to be as a valid kernel, not this, but something like this, where p is any integer. So only these two kernels have been identified as a valid kernel. So it's not easy to look and to say if a kernel is valid or not. But instead, we can use the two well-known kernels or any kernel that is already proved to be a valid kernel and construct few more kernels. So I think we are running out of time for today. So we'll look into the construction of